All right, today we're talking about Chapter 11, Section 2, Permutations. So we talked about counting in the previous section. It was a pretty easy section. You really just, again, you just multiply. The hard part was knowing what to multiply, but unlike previous sections, it was just multiplying. There wasn't anything too fancy. In this particular section, uh, we are going to multiply, but we're going to get fancy though. Right? So we're going to start off with jokes, and this part about the jokes, it bleeds into example one, so it is something that probably shouldn't be skipping here. So let's go ahead and snip all this, and we will briefly go over all of it. Okay, this will be on the first page. Let's go ahead and start here. Actually, no, let's go ahead and snip everything we need to, so I don't have to take a break in between explaining. Alrighty, so starting off, we're going to look at some jokes, and the term joke is used very loosely here. So we open this section with 6 jokes about the book, or about books rather. Right? Here they are: 1, 2, 3, 4, 5, 6. I I didn't think any of them were particularly funny at all, um, except for maybe this one. If a word in the dictionary was misspelled, how would we know? That's probably the funniest one. I don't know. Y'all can read them. But we have 6 jokes here. So we can use the fundamental counting principle that we did in the previous section to determine the number of ways these jokes can be delivered. All right, so you're a stand-up comedian and you decide to steal jokes from everybody. And we can figure out how many different ways we can tell these jokes in what order. All right, you can choose any one of the 6 jokes as the first one told. And then once this joke is delivered, we'll have 5 jokes remaining to choose from. And then once that's told, we have 4 jokes remaining, and we can go all the way down to the last one. And of course, we can see here, for our first joke, we have 6 choices. And then for our second joke, right, since we already said one of them, we now have 5 choices. For our third joke, since we said 2 of them, we now have 4 choices. And then we can see what happens here: 6 times 5 times 4 times 3 times 2 times 1. All right, using the fundamental of counting principle that we did in the previous section, well, it's just 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. So there are 720 different ways to deliver the 6 jokes about books. So such an ordered arrangement is called a permutation. A permutation is an ordered arrangement of items that occurs when, number one, no item is used more than once. Of course, well, never mind. And the order of arrangements make a difference. So it matters what order you put them in, and we can't use them more than once. This is called a permutation. So looking at example 1, let's put this permutation to the test here. So the problem reads, in how many ways can the 6 jokes about books be delivered if Bob Blitzer's joke is delivered first and Jerry Seinfeld's joke is told last? Okay, so we have 6 jokes. Joke 1, joke 2, joke 3, joke 4, joke 5, and joke 6. Okay, so for our first joke, and I didn't really go over the author of these jokes, but looking here, the very first one was Groucho Marx, the second one was Bob Blitzer, the third one was Stephen Wright, the fourth one was Henry Youngman, the fifth one was Jerry Seinfeld, and the sixth was Phyllis Diller. Okay, so we're going to tell 6 jokes, and we want to know how many different ways we can deliver these 6 jokes if the first joke was Bob Blitzer's joke and the last joke is Jerry Seinfeld's joke. So for our first joke, we only have one option. And for our last joke, we only have one option. Okay? However, for the middle 4 jokes here, we have options. All right? Well, for that second joke, we have essentially 4 jokes remaining, right? Because Bob Blitzer's is 1, Jerry Seinfeld's is 1, but they're going to be taking the first and 6th spot respectively. So there are 4 possible choices I can tell the second joke, or 4 possible jokes I can tell second. And then, of course, we can go 3 here, and then 2 here, and then there'll just be 1 left over. Okay, and this is the permutation if we were to um, sorry, if this is the permutation if we were to tell those Blitz's joke first and Seinfeld's joke last. And then of course from here it just becomes multiplication, right? 1 times 4, 1 times 4 times 3 times 2 times 1 times 1. Okay, and that is equal to, can we do this in our head? 4, and then 4 times 3 is 12, 12 times 2 is 24, 24 times 1, and then times 1. So we can tell 24, there are 24 different ways to tell these jokes if Blitzer's joke is first and Seinfeld's joke is last. So let's go back to here. If order did not matter there was 720 possible ways. But by making Blitzer's joke first and Seinfeld's joke last, we only have 24 possible ways. And I'm going to go ahead and snip this little bit over here because it's pretty interesting. Just for fun. Just the way numbers are. Alright, so example 2 reads, you need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books, assuming that the order of the books makes a difference to you? Okay, well, so we'll think about this, again, logically here. We have 7 books, and the first book, we'll put this, we'll say the first book in the, I guess it'd be the row, right, or the shelf. The first book on the shelf, the second book on the shelf, third, fourth, fifth, sixth, and seventh. Okay, so we have our bookshelf, and how are we going to lay them out? Well, for our first book, how many possible choices do we have? Well, we have 7 total books, so we have 7 possible choices to go first. Alrighty, well, for our second choice, one book is already in the first spot, right? So we only have 6 possible choices. In the third spot, we have 5 because, again, well, let's not go there just yet. In the third spot, 2 books have already been used, so we have 5 books remaining, so 5 goes here, and then we can see that this does indeed 5, 4, 3, 2, 1. Okay, and unfortunately, I'm going to do this one in our head. So 5,040. Okay, 5,040. There are 5,040 possible ways to arrange 7 books on a shelf. Now, what if we slightly doubled it, right, to 15? All right, so if we had 15 different books on a shelf and it took you 1 minute for each permutation, so it took you 1 minute to rearrange all 15. Well, it would take you almost 2.5 million years to go through every single permutation, and that's kind of cool, I guess. I mean, what use is that? I don't know, but it's just kind of cool the way numbers are, especially big numbers. All right, so next up we're going to talk about factorial notation. So this is probably going to be a brand new notation for you. A notation that you have not seen before, except for maybe in like genius math movies or something, right? You might have seen this on the chalkboard behind the mathematical savant. Anyway, so they've factorial notation. So we did 7 times 6 times 5 times 4 times 3 times 2 times 1. We did that for the arrangement of books on a shelf. Right. Well, we can write that a little bit more succinctly as a 7. Well, here we go. As a 7 with an exclamation point. And that exclamation point, what that means is you just basically take that, you start that number, and then you multiply everything all the way down from there. So 7, and then again the word is factorial. 7 factorial, you just do 7 times 6 times 5 times 4 times 3 times 2 times 1. All right, and of course you can see how it behaves with all these numbers, right? 4 factorial, 4 times 3 times 2 times 1, and so forth. And that's all factorial notation is. Keep in mind also, 0 factorial by definition is going to be 1. And here are some factorials right off the bat. I'll give you some good news. You don't have to memorize these. Okay, no sense in memorizing these. It's just kind of showing you how the numbers grow super duper fast. Like for instance, from 5 factorial to 6 factorial, we go up 600. From 6 factorial to 7 factorial, we go up 4,300. And then from 7 factorial to 8 factorial, we go up 35,000, and it just goes up faster and faster and faster and faster. 20 factorial is what? It's million, billion, trillion, I don't know, quintillion. I forget. I forget my illions, honestly, after trillion. Um, but it goes up pretty quickly, pretty fast. So let's do some arithmetic here with the factorials. Okay, and this specifically says evaluate the following factorial expressions without using the factorial key on your calculator. Now, many of you probably don't have the factorial key on your calculator, and that's fine. And also, the thing is, I mean, if you have it, yeah, it'd be easier. But if you don't have it, it's still pretty easy, and we'll see why here in a moment. So let's go ahead and start with A to really show why and how it would be that easier. Okay, so 8 factorial. Well, let's just go ahead and write 8 factorial. Okay, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 8 factorial. Well, 5 factorial we know is 5 times 4 times 3 times 2 times 1. Right? And here's where it gets pretty easy, more or less. Well, instead of, and you know what, let's actually just, let's do this for fun. Okay, so let's go ahead and just do 8 factorial. All right, and if we did 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that would be 40,320. Okay, and then 5 factorial would be 120. Okay, now you could do that, 40,320 divided by 120 and figure out the answer, but that's not the point of this exercise. Furthermore, believe it or not, that's actually the long way. The short way is we see that we have 8 factorial in my numerator and 5 factorial in my denominator. All right. Well, we didn't even have to actually write all this out. Okay, we could have just written these three, and here's why. Well, this 5 cancels with this 5, this 4 cancels with this 4, and we see that they all cancel there. So it's essentially 8 times 7 times 6. And what is 8 times 7 times 6? Well, 8 times 7 times 6 is 336. So 336. Okay, so let's think of a rule real quick before we even move on to B. Okay, we're just gonna come up with a rule on our own so we can kind of skip the process of writing all this over this and then canceling. Well, it appears that whenever we had for this particular example, we had 8 factorial over 5 factorial, it looked like, since the numerator is larger than the denominator, it looked like we can essentially just kind of stop at where the denominator factorial is, right? So for instance, A was 5 factorial. Well, we could have just not even written the 5 factorial in my numerator and be done with it. And so let's try to do that for B. So we have 26 factorial over 21 factorial. I will not write 26 times 25 times 24 times 30 23. Instead, what I'm going to do is I know that we're just going to write 26 times 25 times 24 times 23 times 22 times 21. Okay, but I'm going to erase the 21. Why? Well, if we look back at our example A here, again, we had the 5 factorial in my denominator. Well, that was the first thing I canceled in my numerator, was the 5. Well, for B, we have the 21 factorial in my denominator, so that's going to be the first thing that I'm going to cancel in my numerator, the 21. So I'm going to go ahead and erase that 21. Okay, and if that bothers you, here's another way to think about it. Let me go ahead and erase that and put that there. 26 times 25 times 24 times 23 times 22, and then if you wanted to, you could say times 21 and then factorial. Let's fix that a little bit. 21 factorial all over 21 factorial. Okay, and then we're essentially canceling the factorials out. Right? And after a while, saying factorial a lot just does get kind of weird to say. But we could think of it like this as well. Okay, and we actually will. So let's go ahead and just do this. Well, what is 26 times 25 times 24? All that. Let's put it into our calculator. Okay. It is still an enormous number, actually. So let's go ahead and put that down here. Okay, and that's how we did it. And again, we didn't even have to write. We did not even have to write this part up here or this denominator. I just wrote that to show you that we're essentially doing the canceling that we did in A without having to write times 19 times 18 times 17 times 16 times 15 and all the way down. Okay, and nowhere is that more prevalent than in example C here, because it would take an absolute madman to write 500 factorial. Okay, so instead what I'm going to do is I'm going to write 500, and I'm just going to begin the factorial process, times, yes, go for it, what's up? Uh-huh. Yeah, I just looked at my calculator, and I just realized that I did make an error there. Yeah, I typed a 21 instead of 22 into my calculator. Yeah, thank you for that. Yeah, it's actually supposed to be 7, 8. 7, 8, 9, 3, 600. Yeah, sorry about that. For some reason I skipped the 22 and just wrote 21 into the calculator. Oh well, that would be hair pulling if I did it in the homework. All right, so going back to example C now, um, we had the 500 factorial over 499 factorial. Again, it would just be crazy to write 500 all the way down to 1. Instead, I'm going to do 500 and then times 499, and I'm going to write times 499 factorial. And all that over 499 factorial. And this is super duper easy because those obviously are going to cancel. So we're left with just a 500. Okay. All right, so we're going to look at a formula for permutation. I'm going to snip this and put it on the notes, but I'm not going to go over this. This will just be for your own reading pleasure, just to really fully understand it. Um, I mean, I will. I'm going to go over it in a way that we understand it, as opposed to that particular part. Yeah, I mean, I'm not skipping things just for the fun of it. This part right here is what I'm really going to focus on. Okay. Alrighty. So starting with this paragraph right here, we have the notation where we have n and then a capital P and then a little r. Okay. So what this means, this notation, it means the number of permutation of n things taken r at a time. Okay. So looking at for instance, we look over here. We have you're the coach of a little league baseball team, and you have 13 players. We have 13 players, but you need to permute, I guess, permute 9 of them. Okay, so the notation would look like this. It would be 13p9. Okay, that's the notation for it, and that what that notation means we see down here. Okay, so again the 13p9, but then looking, let's go ahead and do this. N would be equal to 13. P, again, that's just a notation meaning permutation. And then R is 9 of them. Okay. So again, you have 13 possible choices, but you need to permute 9 of them. And so we use the formula we see here. Okay. And again, I wrote n being 13, so you'd write 13 factorial, which we see up here. And then n minus r, well, n is 13 minus r, so 13 minus 9 is 4, so it would be 4 factorial. So this particular example here would be 13 factorial over 4 factorial. Okay. Now again, like I said, I just kind of hand wave through that mainly because I want to jump to our example here, where we don't already have the idea processed yet. Okay. So this is maybe I should snip the formula too, just for fun. Okay, so again, this is similar to the baseball thing, and I just don't want to read that off the board. Um, so reading the problem, we have you and 19 of your friends. Okay, so you and 19 of your friends, that makes 20 people, decide to form an internet marketing consulting firm. The group needs to choose 3 officers. All right, a CEO, an operation manager, and a treasurer. Doesn't really matter what the titles are. We're just going to choose 3 officers. Okay, so in how many ways can those offices be filled? Okay, well, we have 20 possible people. Okay, so that's going to mean that's going to take our n. There are 20 possible people. All right, and then the r. All right, of those 20 people, we need to have 3 officers. So that's going to be the r. R is equal to 3. Okay, so the notation here, we're just going to write this as again. Let's what's p and r. Okay, well, we're going to just erase this in and put a 20, and we're going to erase this r and put a 3. Okay, and the formula, all right, if we follow along with the formula up there, all right, it is n factorial. Okay, so it's going to be 20 factorial in the numerator, and then the denominator is n minus r factorial. Okay, well, n minus r is 20 minus 3, which is 17, so you have 17 factorial in the denominator. Okay, and then we can do the arithmetic that we did in the first, well, not the first example, but example 2 and 3, and so we'll write this as 20 times 19 times 18 times 17 factorial. Right, the 17 factorial just basically means, all right, we're just going to go on and on and on, but we're going to write that 17 factorial, and then the notation is gonna be canceled out with the notation in the denominator, which is 17 factorial here. Okay, and of course we can see why we do that now. We cancel out the 17 factorials, and then my solution is just going to be 20 times 19 times 18, which is, hopefully I can do this right, 6840. Okay, so again, just to recap, we have the hard part here is figuring out what is n and what is r. Okay, well, again, the n is the number of items, and the r is how many we're going to the possible permutations of them. Of course, we see that the definition again there. And well, that's it for that one. All right, so this one looks a little tougher. All right, this is going to be one that we have to just kind of think about. It's not hard, but let's go ahead and begin it. So you are working for the sitcom television network. Your assignment is to help set up the television schedule for Monday evenings between 7 and 10 p.m. You need to schedule a show in each of the 6 30-minute time blocks, beginning with 7 to 7:30. Okay, so there are 6 time blocks here, right? So like 7 to 7:30 is 1, 7:30 to 8 is 2, 8 to 8:30 is 3, 8:30 to 9 is 4, 9 to 9:30 is 5, and 9:30 is 6. I'm sorry, 9:30 to 10 is 6. So we have 6 time blocks from 7 to 10. And you can also select from among the following situation comedies or sitcoms. Right? And the sitcoms are The Office, Seinfeld, That 70s Show, Cheers, The Big Bang Theory, Frasier, All in the Family, I Love Lucy, MASH, The Larry Sanders Show, Modern Family, Married with Children, and Curb Your Enthusiasm. Okay, so how many different programming schedules can be arranged? Okay, so looking at this particular problem, we're told we have 6 scheduling blocks here. Okay, well, we need to figure out, first of all, how many sitcoms do we have? Well, counting it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think those 13. I don't know, I'm counting 14. Let's cross them off. How about that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. All right, so there are 13 shows. So this tells me that my n is going to be 13. Okay. And then my r, right, is we know we had 6 blocks, 6 time blocks. So my r is going to be equal to 6. Okay. And let's go ahead and again bring in the formula. Okay, so bring in the formula, and again, so our notation is going to look something like this. It's going to be, let's block that off, 13, so it's going to be 13, and then big P, little r, which is 6, and then just following along with the formula, it is going to be 13 factorial in my numerator, all over n minus r. Let's just go ahead and write n minus r there, I guess. We don't have to write 7 just yet. So 13 minus 6 factorial. Okay, and let's push this down here. So 13 minus 6 is 7, so we're going to end up with a 13 factorial over 7 factorial, which we can write that as 13 times, well, yeah, we're going to do that. 13 times 12 times 11 times 10 times 9 times 8 times 7 factorial, because again, that 7 factorial just basically means 6, 5, 4, 3, 2, 1. But we're not going to write that because we're going to cancel it with my denominator there. Okay, and canceling 7 factorials, we're left with 13 times 12 times 11 times 10 times 9 times 8. And all that is going to be holy cow, that's a lot of permutations. All right, so 1, 2, 3, 5, 5, 2, 0. So 1.235 million different ways. So if I have 6 time blocks and I've got 13 shows, there are 1.2 million different ways that I can put these shows on the air. Um, Seems like a easy task to me. I don't know, it looks like a lot of them you can kind of, if it's Monday, you can have like a throwback Monday or something like that. It looks like, I don't know. All right, so, and the last thing we're going to talk about today is the permutations of duplicate items. All right, so let's go back and look at our definition of permutations real fast. Probably should have done it in the notes because now I got to do this again. Oh shoot. Okay. Yeah, we'll just go look in the notes real fast. These pages take forever to turn. All right. Where are we looking for? All right. So when we talked about factorial, right? And with factorial, when we did, we took, for instance, 7 factorial. We had 7 options the first time, and then once we use that one, we did, I think books was one of them. Once we use one of the books, we now have 6 books left, and then after that we have 5 books left, and so forth. Okay, that's when everything is different. They're all different books. Okay, But let's just say, for example, that you have the same book. No, that's a horrible example. Let's just go with the textbook example. Okay, so looking at the word set. Okay, so set, there are 6 possible permutations for set, right? It's written S-E-T. Well, there are 3 letters, and so you just do 3 factorial, which is 3 times 2 times 1, which is 6. So there is 6 possible ways to write set. All right. Well, now let's look at A and A. Alrighty. So A and A, how many possible ways are there to write A and A? Well, as you can tell, we have a duplicate letter, A. Right? So there's not going to be 6 distinct ways to rewrite A and A because we have a repeating letter. Right? Of course, we see the way they're written here. So one of the A's is pink, one of the A's is blue. And so, for instance, let's just look at AAN. Well, we have a pink A, blue A, N, and then down here we have a blue A, pink A, N. Well, that spells the same thing, doesn't it? AAN. So having that duplicate letter obviously kind of throws a wrench into our idea of permutations. Right? Luckily, we have a nice handy-dandy formula for it. But look, going back to A and A, there are actually only 3 distinct ways to write A and A. Right? So our formula to write A and A, right, is pretty easy. Don't worry, it's nothing abundantly difficult. So rating what's in the sanity area, the number of permutations of n items where p items are identical, q items are identical, r items are identical, and so on, is given by our formula here. Okay. Now, in this formula, we use p, q, and r, and then so on, right? Depending on how many identical, in this particular case, letters we have. Well, if we were to use this formula for A and A, well, there are 3 letters. Okay, so that is the n, so that's n factorial. There are 3 letters. So we write 3 factorial. And then p items are identical, and we're looking at the denominator here. So where p items are identical, q items are identical, r items are identical, and so on. Well, in A and A, we only have 2 that are identical. So we would put 2 factorial. And of course, writing out 3 factorial over 2 factorial, like the same thing we've done in the examples before, the 2 factorials cancel, and so we're just left with a 3. And of course, we do indeed see that there are 3 distinct ways to write A and A. Now, that was a pretty simple example. So let's go look at one that's a little bit tougher and quite a bit more interesting. Mississippi. And let's go ahead and bring the formula with us. All right, so here's the formula. And problem 6 reads, in how many distinct ways can the letters of the word Mississippi be arranged? Okay, so the first thing I need to do is figure out, well, how many letters are in Mississippi? All right, well, counting it, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like we have 11. Let me read counting again just in case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it looks like my n here is 11. We have 11 possible, or no, not 11 possible, but we have 11 letters. Okay, well, we've got quite a few duplicates, right? And so let's go ahead and name these duplicates. All right, one of the duplicates we're going to just name p, well, lowercase p. You know what? Let's just make lowercase p be equal to the amount of big P's. Okay, so how many big P's are there? Looks like 2. Yeah, so 2. All right, and then q, well, how many? We'll do I next. So there are 1, 2, 3, 4 I's, and the PQR. All right, well, how many of another letter we have? Well, we have 4 S's. Yeah, I think that's all the duplicates. I's, S's, and P's. Yeah, that's all the duplicates. And let's say that let's for maybe something ridiculous. You might have a word that has multiple M's, right? Well, in our definition, it says and so on, right? We did P, Q, R, and so on. Well, the and so on basically means, okay, so we can basically say how many M's are there, and let's just say there's 3 M's, right? And you can do this for forever, honestly. But for this particular example, we don't have to do that. we can just stop here. Okay, so by using the numbers that we have in our formula here, okay, so we have n factorial, which is going to be 11 factorial. That's going to be all over 2 factorial, 2 factorial, 4 factorial, and 4 factorial. And I don't really like the way that looks. That looks like hieroglyphics. Let me see if I can make it a little bit prettier. All right, I don't think I can. So 2 factorial, 4 factorial, and 4 factorial. Alrighty. So I probably shouldn't have done this this way, but it's not a big deal. So let's go ahead and rewrite 11 factorial, and let's just go all the way down to what looks like might just be 4, right? Because we're going to cancel it with a 4 factorial. So we're going to have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4, and then we'll put a factorial there. All right, and then that 4 factorial in the numerator can cancel with one of them in my denominator. And so we can now do the arithmetic here, right? Well, let's go ahead and assuming you don't have the factorial button on your calculator, let's go ahead and rewrite 4 factorial here as 4 times 3 times 2 times 1. And let's go ahead and rewrite this 2 in the front as 2 times 1. Okay. So doing all this, 11 times 10 times 9 times 8 times 7 times 6 times 5. That's in my numerator, and then my denominator is going to be 2 times 1. Didn't put a division sign, hang on. 2 times 1 times 4 times 3 times 2 times 1. So we end up with 34,650. So there are 34,650 ways that we can rewrite Mississippi in a distinct way with our I's, S's, and P's actually repeating. So that concludes today's lecture. We got new notation, but we're still in the realm of just doing multiplication. So hopefully that should be easy.